Hi there, I'm Dave Evans, a PhD candidate from the University of British Columbia. In this video, I'm going to talk about JPEG-ACT, Accelerating Deep Learning via Transform-Based Lossy Compression. This work was published in ISCA 2020, and I'll get started with some context of the problem that we investigate. The benefits of increased training performance. If we examine image classification networks, it's useful to look at the relationship between the accuracy of a network and how much computation is required to train it. We can see from recent classification networks that accuracy has improved as training performance has increased. Notably, PNASNet uses an architecture search, which increases the total research and training computation by about 10,000 times. Now, if we focus on AlexNet, which restarted interest in convolutional neural networks, the author, Krzyzewski, has stated that he thought he could use GPUs to ratchet up the processing speed of deep neural networks and create a better algorithm. Usually compute drives these performance improvements, but this can be held back by many things. The pursuit of accuracy has a problem. Larger networks lead to more activations and a higher memory consumption. We use the insight that activations look like images. We can use similar techniques to handle both of them. If we examine prior works on activation compression, we can see that lossy precision reduction results in better performance, but some loss in accuracy. Compressing the activations using JPEG leads to relatively poor results. This is because JPEG uses compression parameters that were tuned for images and human perception. By optimizing these parameters, we improve compression and therefore performance, significantly improving accuracy in our work. Our optimization strategy can be extended to most compression methods. JPEG-ACT is an offload accelerator that takes advantage of this compression through a compressed offload and has no changes to the CNN training procedure, no changes to the network architecture, and uses an optimized compression to minimize accuracy loss. In this video, I'll cover some background information on training, a high-level overview of the JPEG algorithm and why we chose it, the system architecture of JPEG-ACT, the hardware we introduced for the JPEG-ACT accelerator, the optimization of the compression parameters, and the results of our work. Training CNNs with typical techniques requires the storage of a large number of activations. Let's look at how CNN activation size during training has compared to the available memory on graphics processors, or GPUs. Older networks had a very small activation footprint and easily fit onto a single GPU. Newer models were larger and focused on reducing compute, not memory requirements, so needed multiple GPUs to train. And the newest models require many GPUs to train. This gap is due to physical limitations such as bandwidth and memory technology, and is unlikely to improve as accelerators increase compute densities. As for how this problem actually arises, let's look at training with infinite memory on a GPU. There are two phases of CNN training that cause this, the forward and the backward pass. The forward pass produces activations, and then those activations need to be reloaded in the backward pass. The forward and backward pass also use memory for temporary storage, but mainly it is used as a long-term storage, so I'll ignore this for now. One solution to this is by using DNN, which effectively expands the GPU memory by paging to the CPU memory. It does this by offloading activations using memcopy to the CPU memory in the forward pass and transferring them back during the backward pass. There are also other techniques which modify these memcopies or use compression to increase the offload rate or increase the effective memory size, but generally the offload rate is quite limited as the PCIe bandwidth is low while activations are very large. Using stochastic gradient descent and the back-prop algorithm results in a training loop with 3 phases. The edges here represent data transfer between each phase. This is a simple CNN with 5 layers. In the forward pass, the input image is passed through the successive layers, which produces the activations, such as R, C, and N. In the backward pass, the gradient with respect to the loss of each activation and weight is calculated, starting from the last layer and going to the first layer. The weight gradients are then used to update the weights of the network, and the process is repeated. Now, as for activations, they need to be saved, as the gradient computation in the backward pass often requires the activations as an input. The deeper the network, the more storage required for activations. Previous approaches have addressed memory consumption during training, but are limited by their focus on older networks. AlexNet and VGG mainly used a basic block consisting of a 3x3 convolution, ReLU activation, and dropout. Recent networks, for example AmoebaNet, have a much more complicated structure with very little dropout and the introduction of batch normalization. The result of this is a significant decrease in activation sparsity, which drastically impacts the efficiency of sparse compression methods that are used by many prior works. Now we're going to discuss the JPEG algorithm and why we chose it. Our take on the activation problem is to use lossy compression, which is high compression at the expense of fidelity. You can see we have here an image of a cat. and if we discard spatial information, that's discarding some frequencies, we can get a 5x compression ratio using lossy compression with no visible image degradation. If we increase that by turning up the loss, the compression can be increased to 25x and up to 67x, and this is still recognizable as an image of a cat. Now let's talk about the frequency domain and how images and CNN activations are represented in it. JPEG works primarily through the discrete cosine transform, or DCT, which is a subset of Fourier transforms. This converts an image into magnitudes of 64 2D frequency components. If we examine the variation of the frequency components across an image, measured here using entropy, we can see that low frequencies have a much larger variation. I've ordered the frequencies from lowest to highest. The slope profile tells us that there's more information in the low frequencies, or that there's spatial correlation in the image. We see a similar trend with dense CNN activations, implying that there's also spatial correlation, but the distributions are slightly different. We found that spatial correlation exists in all layers of all CNNs that we've examined, even deeper networks. This is a high-level overview of the JPEG pipeline, including the frequency transform from the previous slide, the DCT. Quantization, the primary lossy encoding step, is performed by division, which is a parameterized quantize of the transformed frequency coefficients. The amount of error in each frequency is determined by the JPEG parameters, the DQT, or discrete quantization table. The parameters for JPEG were arrived at by extensively studying human perception. I'll describe later how we adapt these for machine perception. Coding removes zeros introduced by quantization, which further compresses the data. In stock JPEG, this is performed by run length encoding. This completes the pipeline, which produces a compressed image. We will now examine the system setup for JPEG-ACT. Out of the options for training CNNs, ASICs, GPUs, and CPUs, we select GPUs as they have a good trade-off of performance and programmability. However, the memory wall is also applicable to ASICs. Our baseline GPU has streaming multiprocessors, or SMs, connected to a crossbar, and a series of memory controllers consisting of L2 cache and a connection to the GPU high bandwidth memory, or HBM. As well, we connect the GPU to an external CPU using PCIe. This becomes our baseline. In order to improve the offload rate, we add compression to the memory system in the form of a CDU, a compression-decompression unit, which is capable of compressing values from the L2 cache before offloading them using DMA. There are some issues with adding compression at the cache, especially if compression spans multiple memory partitions. This requires sharing data between cache partitions, as well as a large hardware overhead from duplication across the many partitions. Instead, DMA side compression makes a single point of compression for the entire GPU at the DMA unit. As JPEG compression can span multiple cache lines, we choose DMA side compression for JPEG-ACT. Please refer to our paper for more details on CDU placement. We use multiple CDUs to allow for multiple mem copies to be processed at once. This avoids issues with saturating the bandwidth of a single cache partition or crossbar link. The collector and splitter units join and split the streams from the multiple CDUs for the single memory stream. Once again, see our paper for more details. In a system with no CDUs, activation mem copies are performed simultaneously with compute. The CDMA work improves this by compressing mem copies to allow for a higher effective offload rate. JPEG-ACT improves this further by providing compression methods that are capable of handling state-of-the-art CNNs. This significantly improves the offload rate. As we add hardware for compression, we add no extra compute overhead and provide a significantly higher effective offload rate than VDNN or CDMA. We will now go over the JPEG-ACT CDU implementation. This is the design of the baseline compression-decompression unit. In compression mode, during the forward pass, data moves from the crossbar through the CDUs to the collector and DMA. In decompression mode, during the backward pass, data moves from the DMA to the splitter, through the CDUs, and to the GPU crossbar and memory. We use integers in the CDU to avoid operating on expensive floating point activations. We design and implement SFPR, or Scaled Fixed Point Precision Reduction, to convert from floating point activations to integers while keeping truncation errors low. We use an open cores implementation of the JPEG pipeline, which includes a frequency transform and parameterized quantization. We leave the frequency transform as is and modify the remaining components. We modify the div, RLE, RLD, and DQT blocks of the JPEG algorithm to optimize the pipeline for CNN compression. In brief, these changes are designed to increase compression given the value distribution in activations and decrease hardware area. The remainder of the CDU and system is designed to facilitate efficient communication with the GPU memory system by buffering and interleaving data as it travels between the crossbar and DMA engine. I'll now go over our process for tuning JPEG-ACT for CNN compression. We would like to maximize compression while maintaining network accuracy. Starting with some trained network, if we take the compression parameters and simulate compression, then estimate the final network accuracy and JPEG compression ratio, then we could use this to update and optimize the parameters for CNN compression. Note that we are not using this to train the network, we are optimizing to improve the compression. The network training process is not affected in any way. The JPEG parameters are the quantization table, and as for updating, we chose to use SGD for this process. Once again, we are not using SGD on the network, we are using it on the JPEG parameters. We use a network with frozen weights as the input to the algorithm. We use Shannon entropy, H, to estimate compression, which gives the bits required per activation. Estimating the accuracy is much more difficult, as training is stochastic and non-convex. In the paper, we describe an approximation where minimizing the L2 activation error will lead to similar accuracies as training without compression. We combine these two terms into an objective function, with lambdas being scaling factors to adjust the magnitudes. Alpha controls the trade-off between accuracy and compression, similar to the quality setting in JPEG. This objective isn't specific to JPEG and can be used to optimize any parameterized compression method. On average, JPEG-ACT provides a significant increase in performance over VDNN, 2.6x, with significantly improved error versus unoptimized JPEG. If we examine individual network performance, we can see that performance gains are primarily made on networks which include bottlenecks, for example, ResNet 50. Methods focusing on highly sparse networks, such as CDMA and GIST, show poor performance on these deep networks. On average, JPEG-ACT achieves 1.6x performance versus GIST. Now we'll examine compression. On the left, we have various combinations of JPEG backends, and along the top, different quantization tables. If we examine the effect of optimizing JPEG for activations, we can see that optimizing the quantization table significantly increases compression. And when combined with the backend improvements, the compression ratio improves from 5.3x to 7.9x for a 50% improvement. If we look at where these improvements are occurring on VGG, we can see that JPEG significantly improves compression of convolution activations, and by adding zero-value compression and a more aggressive quantization table, compression of dropout and convolution activations increases again. On ResNet 50, as there are no dropout activations, JPEG-ACT has a larger relative compression ratio to the other methods, as 3/4 of the network is dense activations. We see similar trends for the ImageNet and Div2K datasets. Thanks for watching our video. For more information, see our paper in ISCA 2020, or come to our question and answer period at Wednesday, August 12th at 1:15 p.m.